Okay, in this short screencast, there was a question about the importance of curved arrows in organic chemistry. So the curved arrow formalism is a way to basically show how electrons are moving. So a curved arrow is different from a reaction arrow in the following sense. There are two types of curved arrows. The first type looks like this. That would be called a double-headed arrow. And that signifies the movement of two electrons. So when I say two electrons, basically the one head and the second head, that means the two electrons. So we can imagine placing the electrons here, and the arrow is showing where they move to. So this is a double-headed arrow. The other type of arrow is called a fishhook arrow, and that signifies the movement of one electron, also known as a radical. So notice that in the fishhook, we only put one head on the arrowhead here, so double-headed, one-headed is fishhook. So again, the arrow signifies a trajectory of where the electrons are moving to form a bond. So you can think of it as, if you watch football, the quarterback is holding a football, which is a pair of electrons, and the football is being thrown to a receiver. So the trajectory of the football being thrown is similar to how electrons are moving. So that's sort of a sports analogy we can use is just how are the electrons moving? How do we keep count of them? So below I have three examples of where they're used. So the first one would be resonance, where we'll look at this molecule ozone. The second one is a mechanism, where we'll look at an acid-base reaction. The third one is a mechanism where we'll look at a radical reaction. We're going to start by looking at ozone O3. So we know that oxygen has 6 valence electrons. There's 3 of them. So we need to show 18 valence electrons. So I'm going to jump right into this bond line formula here. I've shown 2, 4, 6, 8, 10, 12, 14, 16, 18 valence electrons. I know that these oxygen atoms don't all look like they're in their normal valency, so we're going to have some formal charges involved. Terminus oxygen here is going to be negative, the central oxygen is going to be positive, and this other terminal one is going to be neutral. So again, how do we know that? We know that oxygen forms 1,2 bonds, has 2 lone pairs. The central oxygen has 1, 2, 3 bonds, 1 lone pair, so that's going to have some sort of charge. This terminal oxygen has 1 bond, 1, 2, 3 lone pairs. So again, how do we calculate formal charge? Formal charge is equal to the group number 6 minus the lone pairs of electrons. We have 2. Then we're subtracting off 1/2 of 2, 4, 6. We have 2, 4, 6, 1/2 of the bonding electrons. So that's going to give us a formal charge on the central oxygen, 6 minus 2 minus 3. That gets us our +1. For the terminal oxygen, the formal charge equals 6 minus 2, 4, 6. Lone pair electrons minus 1/2 of 2. That is equal to 6 minus 6 minus 1. That equals -1. So that's where we get those charges from. Now where the curved arrow formalism comes in, if we're looking at any of these lone pairs here with this negative charge, that negative charge can migrate over to the other terminal oxygen. And it will do it in the following way. We're going to show the movement of 2 electrons. So we're using the double-headed arrow. We are now forming a pi bond between these 2 oxygens, and then we're going to break this existing pi bond. So this is called a resonance structure of what we're drawing. So notice that the negative charge moved from one end of the molecule to the other. The positive charge stayed in the middle. That's because its bonding situation really did not change. It still has a lone pair, 2 sigma bonds, and a pi bond. So the curved arrow formalism in resonance, in this case, we're starting the arrow at a lone pair. It's forming a bond between these 2 oxygens. The double-headed arrow means 2 electrons are moving. In this case, we're breaking a pi bond. So we know that a bond is 2 electrons. So the 2 electrons from the pi bond are coming out, 1, 2. We now show those as a lone pair. So notice a couple different type of arrows we see so far. We have a double-headed reaction arrow, or a double-headed curved arrow, a fishhook curved arrow. This straight arrow here with a double head on each side, that's a resonance arrow. So it's incumbent upon you to know what these different arrows mean when we're communicating reaction and structure. So our next example of curved arrow formalism is a mechanism of an acid-base reaction with sodium hydroxide reacting with hydrogen chloride. So sodium hydroxide is a base. Hydrogen chloride is an acid. So fundamentally, the action of a base is to abstract a proton from an acid. So how do we show that? With the curved arrow formalism, the base is supplying 2 electrons, so our arrow starts there, and it's abstracting the hydrogen from the acid. So as I said before, if the base here is the quarterback, the electrons are the football, the arrow is the trajectory the football or the electrons are taking. So we are forming an OH bond. We know that hydrogen can only have 1 bond at a time, so its existing bond has to break. So the 2 electrons in the sigma bond then migrate onto the chlorine. And so what we end up with is water So that would be our conjugate acid, and then our sodium spectator with our chloride anion. So the sodium chloride is the conjugate base on that side. So we're going to review acid-base chemistry in this course as well. That's going to be very important for us for understanding reactions. And so the first 2 examples here have been double-headed arrows indicating the movement of 2 electrons. The last example with radical, what we're looking at is a molecule that has 1, 2, 3 carbons. This is called propane. Then we're looking at bromide radical. So this is bromine, which is neutral. It has an unpaired electron. We're going to show the movement of that unpaired electron to abstract a hydrogen and then form a carbon radical. So we have already discussed and agreed upon that a bond must have 2 electrons in it. So when a bromine radical approaches propane, 1 electron will move. So that's showing the movement of 1 electron. It's abstracting that hydrogen. So 1 electron out of that CH bond is going to bond with it. So we're forming a bond between H and Br. The other electron is then going to move onto carbon and will signify its movement like that. So we're forming a carbon radical plus HBr. So again, this has been a screencast on curved arrow formalism that shows how electrons move either through a double-headed arrow or a fishhook arrow. We've seen how they're employed in resonance, mechanism, acid-base, and mechanism radical.